So, key ideas, let's talk about the written section first and then the multiple choice section. You might want your formula sheet kind of roughly handy. I divide this whole unit into two main ideas: point charges and procedures for that, and parallel plates, or stuff that can be thought of as parallel plates, and procedures for that. So what can I ask you with point charges? Well, for starters, let me see if I can find a good picture here. Sure, this works. Clip. Okay. Here's three positive charges that are fixed as shown in the diagram below. So what can I ask you? Well, I can ask you for the net force on charge Q1? Sure. Okay. How many charges are there? It's a 3. Do I have an equation with 3 charges? No. If they want the net force on charge Q1, then what I would do is I would say, okay, this charge here is either pushing or pulling this guy, how big, direction. This charge here is either pushing or pulling this guy, how big, direction. Okay? So we would find the force between charge 1 and 2, which is K Q1 Q2 over R squared. It's 9 times 10 to the 9th. 4 times 10 to the negative 6. 5 times 10 to the negative 6th, all divided by 0.2 squared. And that's going to give me a magnitude. What direction like charges repel or attract? So this charge is pushing this guy, which is what we're trying to find the force on, to the left or to the right? Then I would find the force between charge 1 and charge 3, which would be 9 times 10 to the 9th, charge 1, charge 3, all over, the total distance is 0.7 squared. Yes, yes, yes. That would give me an answer. This charge here, which way is it pushing this away to the left, or is it pulling it towards the right? Since they're both to the left, I would add these up and the answer would be to the left. So and the units will be newtons. That's what I can do with 3 charges. Most of the time on the written, I'm going to give you 2 charges. Let me see if I can find a nice picture that has 2 charges in a nice straight line. Oh, sure, something like this. I'll even call this part A. So if I want you to find the magnitude of the electric field at point P. Spencer, what do you want me to find? No, the magnitude is what physics quantity, sorry? Electric field, which is what on my formula sheet? Give you a hint, not F for field, that's force. E, okay. And this is between point charges. I'm going to call this charge 1, and I'll call this charge 2. This is creating an electric field. This is creating an electric field. I want to find what they are here where they overlap, the net electric field at point P. So the electric field is going to be, by the way, I'm going to cross out the word magnitude, and I'm just going to say find the electric field, which means I'm going to want magnitude and direction, because it's a vector. I'm going to find the electric field from charge 1. How would I calculate the electric field from a point charge? That's the direction. How would I calculate the magnitude of the electric field? What equation? This is what I'm saying. Look at your formula sheet. Now say it with authority, like you know you're right. How do you know? Point charges around are radius point charge equations. Specifically charge 1, radius 1. It's going to be 9 times 10 to the 9th. Radius 1, charge 1, 8 times 10 to the negative 6, all over. Radius 1 is 4, yes? Squared? You crunch that for me? And we said that electric fields are often in the thousands or tens of thousands or even in the hundreds of thousands. Jessica, you're correct, 4,500 units. Newtons per Coulomb. Direction. So we ignore this charge, temporarily pretend that this charge doesn't exist. This is what you were answering earlier. How do we figure out the direction of electric fields? We ask ourselves a question. If there was a positive right there, which way would it want to move if it could because of that guy? Now we repeat the procedure for charge 2. Electric field from charge 2 is going to be KQ2 all over R2 squared. It's going to be 9 times 10 to the 9th. Alex, am I going to put the negative in? No, not for vectors. We decide the direction. 6 times 10 to the negative 6 all over, its distance is 2 squared. Are you coming back or not? Okay. I'm less mad at you than I was before, but please don't be late. 6, 2, and I get 13,500 newtons per Coulomb. Direction, which way would this move a positive charge if it could? It's attracting. Total electric field is going to be, are these in the same direction, Itzel? So I'm going to have to go winner minus loser. Winning direction is going to be to the left. It's going to be newtons per Coulomb, and I think I can do this in my head. 13,500 take away 4,500 is going to be 13 take away 4. 9.0 times 10 to the third. I was going to write 9,000, but that's only one sig fig, and I don't want to be losing dumb marks for sig figs. So that's one thing I can ask with 2-point charges. What else can I ask you to find? Nope, learned to write, Mr. Dueck. Oh heck, let's type because you've committed to it now. B. Find the electric potential at P. Find the electric potential right there. Did they say find the electric potential energy? No. And because I've scrolled down, I'm going to quickly recopy the diagram. Clip. Dope. Let's try that again. This time let's get that in the foreground. Clip. So what's another word for electric potential then? Wow. Voltage. How am I going to find the voltage there? I'm going to again use what we called the fancy word principle of superposition. Ignore that, find the voltage from this guy. Ignore that, find the voltage from this guy. And then because these ones are scalars, not vectors, I can just add them up. Voltage. Hey Spence, what's the voltage for point charges? Did I say point charges is a letter that kind of tells you that it's a point charge? What's the voltage for point charges? Hey, very nice. This is going to be voltage from charge 1, KQ1 over R1. 9 times 10 to the 9th, 8 times 10 to the negative 6, all over 4. I get a voltage of 18,000. Direction. Trick question. Voltage, scalar or vector? It's a scalar. Find the voltage from charge 2. It's going to be 9 times 10 to the 9th. Alex, am I putting a negative in here? Yep. And its distance is 2 away from location P. Change that to a 2. Change that to a 6. And include a negative. I get negative 27,000 volts. The voltage at location P is going to be 18,000 plus negative 27,000. Well, you know what the voltage is at location P? That plus that. Negative 9,000 volts. Let's see how much work to bring an electron from a very long distance away to location P. I could ask you how much work it takes to bring something into location P. Well, now we're going to go work. Can I use force times distance? No, why not? Because with point charges, the force changes all the time. So, oh, can I find the area under a force versus distance graph? It didn't give me a graph. This is going to be, and I think we're starting and ending at rest in this location, in this situation. Alex, which equation will I use for work here? I would use that. You know why? Because what did I just figure out in part B? And Q is the charge that I'm moving. What charge am I moving? Hey, I know all this. In fact, the amount of work it's going to take is negative 1.6 times 10 to negative 19. There's the charge on an electron. Negative 9,000 volts. And I do get a positive answer because the electron does not want to move towards where that negative voltage is. It would be pushing away the entire time, which means I would have to add energy. I would have to do work. In fact, if I let it go, it would want to go shooting back out to infinity. It would have some kinetic, sorry, the potential would become kinetic again. Whatever the heck this is, times negative 9,000 times negative 1.6 times 10 to negative 19. 1.44 times 10 to the negative 15. Okay. What about one fixed charge, one moving charge? For example, here's a big charge, negative 12. millicoulombs. Did I use milli? Nope, I used micro. Never mind. Otherwise we might accidentally go faster than light, which would be a problem. We're going to start off with a little electron right here. How about 2 electrons right here? 2 little negatives. It's an ionized atom of some type. It's got 2 extra negative charges. So we start out here, little invisible angels holding this guy, invisible angels holding this guy, and these guys let go. Which way will this charge want to move? Towards or away? Away. So let's suppose that it moves to here. And let's say that this is 3.2 meters. And let's say that this is 3.0 meters. How fast? How fast? How fast? Did some coaching on the weekend, my throat's sore. How fast? Okay. What am I going to use here? Yeah. Conservation of energy. Because there's a change in height and a change in speed. Although it's not exactly a height, I can kind of imagine tilting it up and it'd be a change in height, a change in speed. I'm going to start out by going your initial kinetic, your initial potential equals your final kinetic and your final potential. I think we would assume you're starting at rest. And then I would get the kinetic by itself, because that's going to find V final for me. So potential energy initial minus potential energy final equals kinetic energy final. Yes? What's potential energy between 2 point charges, Itzel? And the R initial minus K Q1 Q2 over R final, and that's going to equal a half mv final squared. Let's crunch this and then we'll divide by a half m at the very, very end. K, 9 times 10 to the 9th. Charge 1, negative 12 times 10 to the negative 6. Include the negative because energy is a scalar. We put the negative sign in. Charge 2, negative 2 electrons. So negative 2 times 1.6 times 10 to the negative 19. All over 3. That's my initial radius. Minus 9 times 10 to the 9th. Negative 12 times 10 to the negative 6. Negative 2 electrons. Whoop. All over. Now my final distance is 6.2. Apparently this is going to equal a half mv final squared. I did this last year. Let me make sure I got the same numbers. Hey, I do. I think you get 5.946 times 10 to the negative 15 equals a half mv final squared. Cutting corners here, Kara, because I don't want to take the time to crunch all this. So I think V final is going to be 2 times 5.946 times 10 to the negative 15 divided by the mass of an electron. Square root of the mass of an electron was 9.11 times 10 to the negative 31. Did I type something in wrong here? This isn't what I got last time. Two electrons, thank you. Thank you, Alex. Now I need brackets. Hey, that looks better. Let me include that times 2. 2 electrons. And we get 8.08 times 10 to the 7th meters per second. That's most of what I can throw at you with 2 points. The only other one with point charges that shows up sometimes is, let me see if I can find it. Something like this. This is just designed to make it look a little scarier. It says 2 charges are positioned in the diagram below. Kara, what are they asking me to find here? Work. Okay. I would say that work is going to be change in potential plus change in kinetic, and no change in kinetic. What's the work? To be honest, I would go Q, the charge that we're moving, this big, times the change in voltage. And what I would do is I would find the net voltage right there, which is going to be this voltage plus this voltage. The net voltage right there, which is going to be that voltage plus that voltage. Use V1 initial, V initial equals V1 initial. In fact, are these two distances the same, Spence? Are these two charges the same? Find the voltage from one and double it. Find the voltage from one and double it. Final minus initial times the charge that you're moving. That's probably the easiest way to get there. Okay. So between parallel plates, what can we ask? Show me a good plate question, Mr. Dueck. These are all point charges, point charges. Oh, apparently that's all of that review. Let's go to the old electrostatics review. Could do something like this. 2 metal plates are arranged as shown in the above diagram, one charge positive, one charge negative. if the potential difference between them is 450 volts, what's the magnitude of electric field at point P? So electric field, which we've already agreed Spence is that, has a second definition that involves voltage and the distance between them. What? Yeah. I agree what you said, energy. I gotta say electric field. Change in voltage divided by distance. What's the change in voltage? 450. What's the distance? Not that distance, the total distance. Why? Because between, well, first of all, let's put the 5 millimeters, which is 0.005 meters. What's the answer? The idea, electric field between parallel plates is uniform, the same everywhere, and therefore constant. The voltage changes. The fact that we have 450 volts and 5 millimeters means each millimeter is 450 divided by 5, 90 volts. So 180 volts right there, 270 volts right there. But they didn't ask me anything about the voltage. The electric field is constant as long as we're not on the very, very edges. Speaking of electric fields, you need to be able to recognize an electric field diagram. So I'm going to give you one of these on the multiple choice, something like this. Which of the following correctly describes the polarity of charges X and Y? How can you tell which one's positive, which one's negative? Yep. Electric field goes away from positive towards negative, so which one's positive? Which one's negative? Which one's bigger? It's a trick question. They're both the same magnitude. You know how you know that? Because they both have the same number of what? Lines. If one of these had more lines coming off of it, that would be a bigger charge. In fact, how many lines does this guy have coming in? 1, 2, 3, 4, 5. How many lines does this guy have coming off? 1, 2, 3, 4, 5. If this had 10 lines, it'd be exactly twice as big as that. I don't know how big, but I just don't know the ratio. Okay. So yeah, and to do this one, I would go, that's positive, negative, negative. That's negative, no, and then I would step back and say which one did I put 2 check marks next to. You've seen how I do that for these chart questions, yes? The other place we used plate charges was really in terms of energy transformations. For example, like this diagram here. Except I didn't clip it right. For example, like this diagram here. So an electron initially at rest is accelerated through a potential difference of 600 volts as shown. I think we're assuming it started on the ground, on the bottom. Find the final speed of the electron. Did they say final velocity, Itzel? No, what did they say to find? Final what? That suggests I probably want to do this with a scalar approach. Energies, energies, energies. In fact, I'm going to say the initial kinetic and the initial potential equals the final kinetic and the final potential. Oh, initially at rest. I didn't have to do that. I would feel comfortable not doing that on your test, giving you an initial kinetic energy or an initial speed. What else is 0 here? Alex? You fall into the ground when you get to the top. In fact, we're going to get a half mv final squared. And here, this is the equation where we said QV. Now this equation is not blatantly on your formula sheet. What is on your formula sheet is that voltage, or change in voltage, equals change in energy divided by Q. So I'm going to expect you to be able to rewrite it. This was the equation that had the V and the other V in it. This was the equation where we ended up getting V final equals 2Q voltage divided by the mass. It's going to be 2 times 1.6 times 10 to the negative 19. $600 divided by 1.6 times 10 to the negative 19. No, mass is not that, Mr. Dueck. Mass is 3.1. 9.1 times 10 to the negative 31. Is that right, Jess? Sorry? Ah, Jessica. I thought I'd gotten away with it this year with no one asking and trapping me. I should have counted on you to catch that. So Jessica says, hey, Dueck, shouldn't you put a negative there because it's a scalar? Here's the problem. If I put a negative there, can I take the square root of a negative? And I don't want to have my calculator crash. Okay. This one here, I ditch the signs because I know my final answer is supposed to be positive. I think what we are supposed to argue is that as we are climbing up, we are going through a negative voltage, but I'm not sure because other situations that makes sense to me to be positive. So all I'm going to say to you here, Jessica, is, you know what, when you get to this line, do you know the final velocity is supposed to be, this final speed is supposed to be a positive answer? Say yes, then chuck the signs because we know. That's not a great explanation, but that will have to suffice. What'd you get, Kara? Oh, I got that? Yes? No? 1.45 times 10 to the 1, 2, 3, 4, 5, 6, 7. Yeah. $550. Yeah. So this was, then the net voltage would be 550. If it was negative 50, the net voltage would be 650. Hey, just for theory, what if we had a proton starting up here, falling down? Would it gain the same amount of kinetic energy? Well, let's see. The kinetic energy gain was equal to QV. Does the proton have the same charge as an electron? Did it go through the same voltage? So it would gain the same amount of kinetic energy. Would it be going as fast? You said no. Why not? Proton has way bigger mass. This is the same. That's the same, but a bigger mass. Yeah, it wouldn't be going as fast. Okay. Other ways that I can mix and match, give it an initial speed. We did that in the homework, yes? So, having said all that, any weird questions from the review that you would like me to go over? Oh, by the way, really quickly then, what's the answer for number 1? Which of the following best illustrates the electric field between parallel plates? What did I tell you the electric field was between parallel plates? Constant. How do we show that with field lines? Same what and same what? Same direction, yes, and same width. Now, which way do electric field lines always point from what to what? Okay, so that's what. I know that's wrong. I know that's wrong. That's wrong because it's pointing from negative to positive. Yeah. We talked about the cathode ray tube and the deflection and all that. So, let me find another interesting one. So definitely something like number 7. I like finding the potential at a location when there's 2 charges, 2-point charges. Remembering that potential is another word for voltage, not energy. Asking you to find the net electric force. Now this one's a bit tricky because they're giving you D and D over 2, and they're not telling you the magnitudes of the charges. Well, all the charges are identical, so I might let them be 1 millicoulomb or 2 microcoulombs or something like that. Oh, what might be a smart number to pick for D, distance? If you didn't want to do it algebraically, and you're just trying to see 2, that would make this distance here, and the total distance 3, and let the charge. I would do this algebraically because I'm a nerd, but if you couldn't do it algebraically, sure, let the charges be 2 microcoulombs or 1 microcoulomb or 3 microcoulombs or 10 micro or whatever. But it does say they're all identical, so we use the same number, and you can calculate the net force. We did a net force on 1 charge from 2 other charges earlier in this tutorial. Number 12 I like, finding the electric field between 2 charges. Hey, did you guys get number 15? So it's kind of a neat one. I'll show you my answer key. Kara, here's what I said. This is becoming more and more positive as we travel to the right. Yes? So this positive charge, because it's a proton, is going to get more and more and more repelled. So what I asked is, how much potential energy does it need to use up its kinetic energy? And they did tell me its kinetic energy was that. Is that okay so far? Oh, in other words, I said whatever potential energy I lose or I gain, this kinetic energy I lose here. But Jessica, I'm ignoring the signs because I know the magnitudes would be the same. I said, well, potential energy is Q change in voltage. Kinetic, they told me. Oh, and I know Q on a proton, yes. So I divided by Q, and I said, well, once I've hit 131.25 volts, that's when all of my potential has become kinetic. In what section am I going to run into 131.25 volts if I'm starting at 0 here? Section L. In fact, it would go right here, it would come to a stop for a split second, and then it would start getting repelled back. Sort of like throwing something up and having it come back down. Instead of a height, we found the bolt. So that's kind of a neat one. 16 I like. $17 I like. So here's an electron with the electric field to the right. Which way will the electron feel a force? You're right, I think. West. Because the proton would feel a force to the east, because we said the electric field is which way would a positive or a proton want to move if it could, which means an electron would want to move in the opposite direction, to the west. Sure. 19 is fine. 20 is good. A and B. Okay, so I'll ask you some kind of multiple choice question about electric field lines between point charges. So something like this, or the one that I showed you earlier. Something like 23 again as a written or multiple choice. So 24 is an example of the one that I gave you where they don't line things up just to try and scare you, but because it's asking how much work, and work is a scalar, I don't care that this isn't Alex in a nice straight line. I'm still going to go work is change in potential. I think no change in kinetic because it says moved from. And the change in potential would be the potential energy right there, potential energy right there, final minus initial. I don't need this distance here. I don't care about this distance here. It's a scalar. 27 is fine. 28, sure. Now, what is A asking me to find? Itzel, can you read 28A to me? Find the what? Energy? No, voltage. At point what? And point. What is B asking me to find? For 1 mark, and there's your hint, part of it. What's the word difference mean in math? You subtract, you know what? It wants you to go VB minus VA, or VA minus VB. That's why it's 1 mark, because you've done all the math. You're just going to subtract your 2 answers. Then it's telling you how much work was done, and as a twist, it's saying, okay, if it took that much work, was the charge that we're moving negative or positive? Well, first of all, I think I can figure that out. If it took positive work, it did not want to move to B. What magnitude of charge, what polarity of charge would not want to move to the right because there was a negative right there? You know what? I'm sure charge Q is positive. And then I could, as a twist now, solve for Q instead of solve for the voltage. This time I know the voltage, and I'd be solving for Q. Look at my answer key if you're stuck. Um, 32 is fine. Well, 32A and B, well, okay, I've done one lesson on circuitry, so it's 32C is now fair game. You technically know what a battery looks like and which side is supposed to be negative, which side is supposed to be positive, but I wouldn't put that on this test yet. At the end of the year, I'd feel good. Yeah, here, 33 is a classic example. Here's some electric field lines. Tell me which one's negative, which one's positive. 35, magnitude and direction of electric field. And if I give you the force on a charge, what's the magnitude and polarity of that charge? Another electric field question. Tell me the polarity. So they get fairly repetitive after a while. Oh, here's one, number 40. Electric field lines always point from positive to negative, so this goes from positive to negative, this goes from positive to negative. Why is C wrong? Why is D right? Yeah. Widths, yeah. We said that the way we'll represent electric field lines is their closeness is their strength, so they should all be the same distance apart to show that it's the same magnitude, the same strength. This one's a little wonky. 43 is good. Cathode ray tube, I don't think I'm going to ask too much on it. That's going to be at your final exam, because we're going to be doing the cathode ray tube again, but with magnets, because that's really how they do it. I talked about 46. Another electric field question. I've done a gazillion of those. Scholarship, see, so number 48, I think A is now perfectly fine, because you know a hydrogen is 1 proton and 1 electron. So you know the mass of the proton, you know the mass of an electron. You can get the electric potential energy, it's KQ1, Q2 over R. You can get the kinetic energy, a half mv squared. How can you get a half mv squared? I would, you know what, 48A is fair game. 48B, it's orbiting, so it's moving in a circle. In this case, you would go Fc equals F electric, not not F gravity. So that's an advanced question. But certainly 48A is fair game. Yeah. $50A I think is okay. A little tricky, but I wouldn't consider that crazy off the charts. I wouldn't give this to you as a written. I'd feel comfy as a multiple choice. Nasty. B I wouldn't worry about, although that's nerdily cool. And C I wouldn't worry about either. Okay. Any questions from the reviews that you were wondering about? That I said I'd do that and I didn't really do that. I went through a bunch of them. So if you're looking for extra practice, I did send out this one along with a solution key, and this one along with a solution key. You'll find there's some overlap between this one and the one I actually gave you, but this one here is all stuff from the 80s that was never electronicized. In fact, let's see, can I find an 87? Show me June 87, Jan 88, Jan 89, Jan 87, June 89, June 86, because I wrote June 87, it would be the exam that I wrote. June 1990, 1990. What do they got against 1987? It was a great grad year. Oh, I guess my exam's not good enough to be on there. We okay? So, practice it. I'll email this all home. Does anybody want a copy of this printed tutorial? If you'd like me to print this up for you right now, I can. No one? Even more gooder. Right click.